This is the next video and a chapter on atoms, molecules, and ions. We just finished talking about chemical symbols and how to avoid writing out the full name of the element and the full number of protons, neutrons, and electrons. So in this series, we'll talk about the mole and how to avoid counting out every single atom in a group of atoms. So we'll start with how to count atoms. As we have learned, atoms are super duper small. Specifically, they are too small to see with your eye. And that makes them difficult to count. Too small to see by eye. So we need an easier way to count how many we've got. All right, so new strategy is in order. And you may never have tried to count atoms before, but I can imagine one thing you probably have tried to count, and that's pennies. So I am attempting to draw a piggy bank. Hopefully you can tell what this is supposed to be. There's the money slot. There are some legs. Here is a caption in case it is totally unintelligible. Piggy bank of pennies. Let's say you've been collecting pennies in here for a while and you're ready to take them to the bank and figure out how many you got. So you pour them all into a big bag, lots of pennies in here, tie it with a twist tie, and you want to know how many pennies are in that bag. So we have several options for counting pennies, each of them less work than the next. So if I want to count how many pennies, let's start with the most obvious choice. The most obvious way to count how many pennies there are is just to count them. It will take you a long time, however. This is not a very efficient way of figuring out how many pennies are in the bag. But it'll work. So if I sat down and I counted all of these pennies, let's say that we counted 576 pennies in the bag. That would probably take you half an hour to count that. So it works, but I think we can do better. I think we can find a faster, more efficient way to do this. So trying again. Slightly faster way of counting pennies. What if instead of counting every pennies, we counted every dozen pennies? Because a dozen is bigger than a single penny. And then after we knew how many dozens there were, then we could convert to pennies to find out how many pennies there were. And so to do a conversion, we need to have a conversion factor. So we need to know how many things are in a dozen. Most of us should know that already. 1 dozen things is 12 things. And this is things, this is kind of like, can be interpreted to mean whatever you want. So 1 dozen could be 12 pennies, 12 pizzas, 12 atoms, 12 people, whatever you want. So 1 dozen things is 12 things. So if I was going to count my pennies in dozens, I would count that there would be 27 dozens of pennies. And 48 doesn't take as long to count to as 576. So I would say that's a little faster. And then I need to take my dozens and convert to pennies. So I'll use that conversion factor to do some dimensional analysis. So I start with what I know, 48 dozen. I put in a conversion factor and I put what I have on the bottom, which is dozens. And I put what I want on the top, which is my things. Or in this case, my things are pennies. And then I put in numbers. So I know that 1 dozen pennies, 1 dozen is 12 things. And so when I multiply, dozen will cancel with dozen, and it will be just pennies at the end. So 48 times 12 should still give me 576 pennies. So, thoughts? How was that? I thought that was a little bit better. I only had to count to 48 this time, and then I had to do a little bit of quick math. So I think overall it was faster. However, somebody had to sort those pennies into dozens. Somebody had to sort them into piles of 12. And if you haven't got a little sibling around to do it for you, it's probably going to be you. And so you really had to count to 48, do a little bit of math, and sort the pennies into piles of 12. So this is still not super efficient because I basically had to count them in order to sort them. So I'm going to try again. I'm going to try again to think of a faster, easier way to count all of these pennies with the least amount of work. And I'm thinking that instead of sorting them into groups, I can weigh them. I can take the mass of my pennies. So I can weigh the bag, figure out how many pennies are in the whole bag. Then I can convert to dozens. And then I can convert to pennies. Brilliant plan. Brilliant. But we're going to need some information to make this work. We're going to need a scale, obviously, so we can weigh the bag, but we also need a conversion factor for this. So we can find the mass of the bag, no problem. This is chemistry after all. We have balances. So let's say the bag is 1,440 grams. I'm going to need a way to convert from mass of the bag to dozens of penny. So I need some sort of a conversion factor with grams on one side and dozens on the other. And that's pretty straightforward to make. All I need to do is count out 1 dozen pennies and take the mass of this. So put 12 pennies on the scale and you'll find it weighs around 30 grams. So that gives me a conversion factor with the grams and dozens in it. And I already have the conversion factor from dozens to pennies. That one we used up here. So this is looking like it's going to be less counting for me, and that is ideal. So we're going to start with what we know. Mass of the bag, 1,440 grams. Then we're going to convert from the mass of the bag to dozens. So I'm going to go from grams to dozens. We put grams on the bottom so it cancels, and dozens on the top. And then the numbers that go with these come from my conversion factor. So I weighed 1 dozen pennies, and 1 dozen pennies weighed 30 grams. Okay, so this is gone. And if I stopped here and I multiplied 1,440 and divided it by 30, I would get 48 dozen, which is what I got up here. But it's fastest to do all of the dimensional analysis steps in one long line. So I'm just going to keep going in this line. So now I have dozens of pennies and I want to convert to pennies. So I put dozen on the bottom so that it cancels, pennies on the top. Then I put in my numbers. I know there are 12 pennies in 1 dozen. The dozen is going to cancel. And now my unit is going to be in pennies. So 1,440 divided by 30 times 12 is 576 pennies in the jar. And looking back, this is the best method yet. All that I had to do was count to 12 and weigh 12 pennies and do a little bit of math. I didn't have to count very high at all. I only had to count and weigh 1 dozen pennies. So you may be saying to yourself, why exactly did we spend 10 minutes talking about how to figure out how many pennies are in a piggy bank? And the answer is that counting a giant number of pennies is not that dissimilar from counting a giant number of atoms. It's just that there are many, many, many more atoms than there are pennies in a piggy bank, and the atoms are much, much, much smaller. So it's even more important to have a strategy like this that optimizes the process so we don't have to spend literal entire lifetimes sitting and counting atoms that are too small to see. So let's talk about how to use that same strategy to count numbers of atoms. So there are millions of atoms in a single spoonful because they are very, very, very small. And because of this, if we ever need to count atoms, counting them by the dozen doesn't really make sense. We need to count them by some unit that's bigger, by the hundreds, by the thousands, by the millions, because there's so many of them in just a small amount of volume. So we need to measure with a quantity much larger than a dozen. And we actually need to measure by a quantity so large that we didn't have one yet. Some scientists had to decide or define what would be a good number for that new quantity. So our original quantity was the dozen, and one dozen had 12 things in it. And now we're going to measure by a new quantity, and that quantity is called a mole. And one mole has 6.022 times 10 to the 23rd things in it. And that was defined by Avogadro. And he did that. He picked that number because that is the number of moles, the number of atoms, sorry, in 12 grams of carbon-12. So this number is so important to chemistry that it has a name. It's named after the guy who invented it, Avogadro. It's called Avogadro's number. And it even has its own symbol, capital N with a subscript capital A for Avogadro. And this number is really important because there are so many atoms in such a small volume that counting it by 12s would not really improve it. So instead, we're going to count atoms by the 10 to the 23rd. And I just want you to take a moment to think about how so large 10 to the 23rd things is. You probably don't know of anything else that there are 10 to the 23rd things of. That's more people than there are on the planet. That's more miles than it is to go all the way around the Earth many, many, many times. 10 to the 23rd is really large. So how large is it? How big is Avogadro's number of things? So let's do another thought exercise. Let's say we have a spoonful of water. A spoonful of water is about 1 mole of water molecules. Because 1 mole of water molecules is 18 grams. We'll talk about why that is in the next video. So 18 grams of water is 1 mole of water molecules. How many molecules is 1 mole of water molecules? Well, if we took these molecules and we distributed them between all of the people on the planet Earth, they were distributed evenly among Earth's population of 7.8 billion people. whoops, not 7.8 people, 7.8 billion people. So if we distributed 1 mole among 7.8 billion people, how many would each person get? Each of those 7.8 billion people would receive 70 trillion molecules, which is still an almost unfathomably large number, but at least is more reasonable. So 7.8 billion people would get 70 trillion molecules. So 10 to the 23rd is like 6 trillion billion things. So it's much, much larger than a dozen. But it's a useful unit to use to count very, very, very small, very, very, very frequent things. So let's talk about what we're going to do with this ginormous quantity that we've just defined. And that is, when we were measuring pennies, we wanted to know what was the mass of 1 dozen pennies. So to measure atoms, we need to know what is the mass of 1 mole of atoms. And you might have guessed that because each atom of each element is different, with differing numbers of protons and neutrons in them that contain the mass of 1 mole of atoms depends on what element it is. One mole of water molecules is going to have a different mass than 1 mole of just oxygen or 1 mole of just hydrogen. So we are going to call the mass of 1 mole molar mass, which has the chemical symbol mm and a unit of grams per mole. So how many grams does 1 mole of some compound have? And you can find the molar mass by looking in our favorite place, in a square of the periodic table. So let's look at carbon again. There was carbon. It had its atomic number, had its full name listed here. And then it had that 12.011 that we talked so much about in a previous video. And we said that was the atomic mass. And in a brilliant move by Avogadro, this number is also the molar mass. So the molar mass, with a unit of grams per mole, has the same value as the atomic mass. With units of AMU. So the reason that we define atomic mass units and moles with the same number is so that this number in the periodic table could indicate both of them. So we learned about the atomic mass before. And we said the atomic mass was this number, 12.011, and it represented the number of atomic mass units in 1 carbon-12 atom. So it was the mass of 1 individual atom. The same number is also the molar mass. So 12.011 is also the number of grams of 1 mole of carbon-12. So this number is both the mass of 1 carbon atom, an atomic mass unit, and the mass of 1 mole of carbon atoms in grams per mole. No, that's kind of a lot to take in. This one number in the periodic table has so many different meanings. It's related to the mass number, it's related to the isotopes, it's related to the atomic mass, and it's related to the molar mass. So in the next video, we are going to do a few calculations to demonstrate how to use that number. But before we do, let's revisit our atoms first approach checklist and check off what we have learned. We have just learned everything we need to know about elements and how to count the number of atoms of a particular element. So we'll check that off in the atoms section.